The speed of light is exactly 670,616,629 miles per hour, or 299,792,458 meters per second, and is believed to be the fastest speed in the universe. To put that into perspective, light can travel around the entire Earth over 7 times in just 1 second. But that's actually quite slow. It only appears fast to us since we're just a microscopic dot in an infinitely large universe. Let's look at the speed of light from a much larger perspective. Although first, we need to understand a few things about light. Light was the first thing created in the universe, but what is light made of? Light is electromagnetic radiation. However, most people connect the term light with visible light, which is what your eyes are sensitive to. But visible light is only a very small portion of the electromagnetic spectrum. Besides visible light, the electromagnetic spectrum also includes gamma rays, X-rays, ultraviolet, infrared, microwaves, and radio waves. The wavelength of light is what determines its category, or in the case of visible light, its color. But what is electromagnetic radiation? Electromagnetic radiation, or light, is propagated by small particles known as photons. Since light is actually a physical object, or more accurately, billions of tiny physical objects, light does actually apply force to any object it hits. However, since light is so, light, this doesn't have much of an effect on a large scale. So, no, you can't put a laser pointer under your car in place of a jack. Unlike other sections of the electromagnetic spectrum, which are most often observed in black and white, visible light is observed in a whole variety of colors. The best demonstration of this is in the rainbow. Although most people think there's 7 colors in the rainbow, there's actually much more. What we observe as colors are actually just different wavelengths of visible light. So red is the longest visible wavelength, and violet is the shortest visible wavelength. And of course, there's more than just 7 wavelengths in between those two. The primary colors of light are often confused with the primary colors of ink. While the primary colors of ink are cyan, magenta, and yellow, the primary colors of light are red, green, and blue. In fact, magenta doesn't actually exist anywhere on the electromagnetic spectrum. Magenta is actually a combination of the shortest and longest ends of the spectrum. While I could go on forever about what exactly light is and how it works, we should probably move on. How does the speed of light compare to the speed of sound? The best representation of just how much faster the speed of light is compared to the speed of sound is seen every time there's a thunderstorm. When you see a flash of lightning that's say 10 miles in the distance, you see it just 54 microseconds, or 0.00005 seconds after it actually happened. Yet the thunder, or sound, takes over 47 seconds. That's nearly 1 million times slower than light. So if light is so much faster than sound, then how is the speed of light so slow? Well, because we've just been looking at what happens on our own tiny planet. There's still a whole universe out there. And when the speed of light is compared to the whole universe, it becomes a snail's pace. Let's board a newly invented spacecraft that is capable of traveling at the speed of light. We'll call it the EMRC, short for electromagnetic radiation, and C, which is commonly used to represent the speed of light. We'll start on Earth and begin exploring the rest of the universe. We should probably do a quick flight around the Earth first, just to make sure all our systems are working correctly. That was pretty quick. About 0.134 seconds to make that flight. Anyway, it looks like the systems are working fine, so let's head to the Sun next. It's our closest neighboring star, so this shouldn't take very long. Okay, this is taking a while. Let's fast forward a bit. And we've arrived. According to our clock, that took a little under 8 minutes and 20 seconds. Let's zero out our stopwatch here and compare everything to their distance from the Sun. Alright, let's head to the orbit of Neptune. We just went from the Earth to the Sun in a few minutes, so this shouldn't take too long. Let's fast forward a bit. Okay, I guess I was wrong again. It's already been an hour and we still haven't reached Neptune. I guess we'll have to fast forward even more. Well, that was the most boring ride of my life. Over 4 hours and we've finally reached the orbit of Neptune. Alright, let's head to Proxima Centauri, our second closest neighboring star. It's quite a ways away, so it will take at least a few months to get there. Well, it's been a year and we're still not there. I guess we'll have to fast forward even more. And we've arrived. That took about 4 years and 3 months. I'm beginning to think this tour is gonna take a bit longer than expected. Let's take a trip to Sirius, the brightest star in the sky. Other than the sun, that is. Well, here we are. Looks like that took us about 8 years and 8 months. Crazy that we were still traveling at the same speed that allowed us to fly around the Earth in less than 1/8 of a second. Anyway, let's continue our journey. Looks like our next stop is Rigel. I think it's quite a ways away, so let's switch to our engines that can propel us at 100 times the speed of light. I know we're going at 100 times the speed of light, but this seems like it's taking a very long time. I think we're going to have to fast forward quite a bit. Okay, that's Rigel. It took us 8 years and nearly 8 months to get here, at 100 times the speed of light. Worst part is, we're not even close to the edge of our own galaxy. So, let's travel to the edge of our galaxy. Let's switch engines again. This time, we'll travel at 10,000 times the speed of light. And here we are, the edge of the Milky Way galaxy. It took us 2.5 years to travel here. And believe it or not, that was only about 1/4 of the distance across the entire Milky Way. Alright, it's time we see just how slow the speed of light really is. This time, we're going to switch our engines to 1 billion times the speed of light, which is over 186 trillion miles per hour. Let's use this new speed to travel in a circle around the entire observable universe. I hope you're ready for a very, very long journey. It's now been a century, but we're not even half done, so you might want to take a knitting or something. Alright, we've now finished our trip around the entire observable universe. It's been nearly 300 years. Let's switch our clock back to light years so we can better compare to travel around the Earth. Wait, what's that number? Oh, yeah, we were traveling at 1 billion times the speed of light. Remember how the speed of light when compared to the universe becomes a snail's pace? Well, a snail could travel around the entire orbit of Neptune over 3,000 times before light could travel around the observable universe once. So either the speed of light is extremely slow, or the universe is extremely large. In fact, it could even be both.